My name is Saad Faizi and I am from OVIP Arab and Partners Hong Kong Limited. I'm here today to present insights from our paper titled Review of Analytical Methods and Recent Advancement in Slope Stability Analysis. In this paper, we discuss some current analytical methods and propose a new approach to refine on existing methods. We also share our recent advancements in automating slope design workflows. This paper is co-authored by Usman Majid and Ryan Say from Arab Hong Kong and Carol Matthews from Arab Newcastle, UK. Slope stability analysis is a critical aspect of geotechnical engineering and are important in various applications, including the design of retaining walls, excavations, and embankments, upgrading of natural slope, among others. Current geotechnical practice widely adopts the method of slices, such as Bishop, Jambu, Spencer, and Morganson Price to analyze slope stability using limit equilibrium. These methods divide the slipping mass of slope into several vertical slices, onto which equations of static equilibrium are subsequently applied. The different methods differ fundamentally based on the conditions of equilibrium they satisfy and their assumptions regarding the interslice forces involved. Several studies and publications have investigated the merits and deficiencies of the different limit equilibrium methods. And while they do all point out some fundamental limitations of the different methods, especially the simpler methods of Bishop and Jambu, these studies also have noted that the errors in the calculated factors of safety from these simpler methods are usually small and on the safe side. However, these are situations in which these relatively simple analytical methods may encounter issues. Authors from past studies investigated the formulation of Bishop method and its implication in various slope scenarios. They noted that the Bishop method may incur numerical difficulties and provide misleading answers in special instances involving interlock. Other methods like Jambu and even Spencer methods may incur similar difficulties in dealing with this interlock phenomena. So what is this interlock phenomena? Well, the interlock arises in the case of a deep slip with a low factor of safety, where the toe of the slip surface passes steeply through a highly cohesive or a highly dense granular material. If a deep slip emerges at a steep angle and has a high cohesion or high mobilized angle of friction, then the direction of the resultant on the base of the slice may be almost horizontal or even pointing downwards, as shown here. To satisfy equilibrium of this slice, the interslice force must point upwards. This direction is not consistent, however, with the assumption of either a horizontal or even parallel inclined interslice forces. In such cases, the inclination of the interslice forces should be allowed to vary to act and correct the direction and take interlock into account. Arab has developed a method whereby Bishop and Jambu methods are refined further by enabling the inclination of the interslice forces to vary. Under this approach, the program calculates the interslice forces to maintain horizontal and vertical equilibrium of each slice first. The inclination of the interslice forces are then varied in each iteration until overall horizontal, vertical, and moment equilibrium is also achieved. Two case examples from past studies are taken to investigate the interlock effect and the use of variably inclined interslice forces. In this first example you see from a past study, the authors exemplified the difficulty of employing the Bishop method by investigating the results of slope stability analysis for an embankment made of a highly cohesive soil. While a good agreement was noted between the ordinary and the Spencer method, the results from the Bishop method was noted to be unreasonably low. This was possibly due to the high cohesion involved. This case example was replicated and reran along with an additional analysis using the Arab method. Results obtained from the Arab method was noted to be reasonable and consistent with the ordinary and Spencer methods from the original study. Similar investigation is also performed on another case example presented in the paper in detail. Hence, we can see how the Arab method offers refinement on existing methods and enable more reliable slope analysis. Similar benefits to slope designs can also be achieved if existing design procedures are streamlined. Fortunately, Oasis Slope does offer designers the opportunity to automate design workflows using customized coding. Let us better understand how automation is made use of by mapping the design workflow for soil nailing works. A typical workflow for carrying out slope upgrading design, shown here, is separated into different stages. Using the results of the initial analysis, an engineer can determine the need for slope upgrading or stabilization through soil nail. Given that the design workflow of soil nail involves several design parameters and detailed calculation of bond strength based on specific slip surface, it requires several manual calculations, and any updates made to any of these key parameters or even a change in the critical slip position would require manual updating of these several calculations performed. Automating this crucial part of the design workflow can greatly assist an engineer and minimize chances to errors due to manual handling. Oasis Slope facilitates automation of soil nail design through two distinct ways. Firstly, it provides the option to calculate the bond resistance of the applied reinforcement members based on the effective overburden stress of the slip surface. Secondly, it includes an application programming interface, or API, that allows the user to interact with the analysis software using different programming languages like VBA or Python, instead of going through the graphical user interface. Once the API has been set up, users can pass relevant data to Oasis Slope and remotely run analysis through calling its built-in component object models, or comp functions. An outline for an Oasis Slope automation framework is shown here, which is used to perform design iterations using VBA as programming language and Microsoft Excel as an intermediate data storage and control interface for running through the analysis on Oasis Slope program. Slope analysis can then be looped using the VBA scripts until set determination criteria is reached, and optimization and sensitivity analysis can hence be easily performed for different parameters. Outputs can also be conveniently extracted in user-defined formats through relevant scripts and functions. Here we see some of the glimpse of various automation tasks, including iterations, optimization, and sensitivity checks that have been performed for the user with ease and efficiency. It is hence evident that by automating key tasks in a slope design, the workflow can be streamlined and made more efficient, allowing users to test a large number of design scenarios in less time. Increased model output allows a more comprehensive understanding of the slope's condition, while any change made to the design parameter can be quickly incorporated to swiftly update the upgrading design accordingly. Indeed, it would not be wrong to say that with the advancement of automation, endless opportunities to improve slope design and analysis can arise. And we just show one example in this current slide. Here you can see just one of the many possibilities that can be explored and assessed by using these automation tools. To sum up, in this study, we have presented ways to improve slope stability analysis and streamline slope design by explaining the use of variably inclined interslice forces to take into account the interlock phenomena and provide sensible results, while also demonstrating our development of a digitalized and automated workflow for slope design that allows streamlining of the workflow along with optimization of design through rapid parametric study. These indeed are promising ways to pave way for better slope engineering, design, and practices. And with this, I conclude my GED talk. Thanks, everyone.